In this video, we are going to learn how to do half-life and decay rates. Now, if you've taken Math 30-1 or even Math 30-2, you would have done some half-life and decay calculations. But in this lesson, we're going to look at the more scientific and the theory behind half-life and decay and a little bit more definitions. Now, many of you know of the negatives of radioactive decay and half-life, for instance, Chernobyl and Fukushima. But there are also some positive things. For instance, have you ever thought of how do archaeologists tell how old bones are? Or why do you get injected with radioactive dyes when you're going for certain things like a CT scan? Scientists have also been using radiation to fight malaria. How to do that? Well, they've been using alpha and beta decay, which is mostly ionizing radiation, to help sterilize mosquitoes that carry malaria. So they're sterilizing the male mosquitoes. So there are some benefits to humans by using radiation, as well as some catastrophes that has caused. Although we cannot tell the exact time of when a nucleon will decay from the nucleus in an atom, what we can do is we can predict very accurately the probability of when it will decay. By knowing these predictability rates, we can apply a fairly simple mathematical equation with nuclear reactions of alpha and beta decay that allow us to use these techniques all over in society, like what we talked about earlier. So first we have to know some terminology. The first one is half-life. So half-life is defined as the time it takes for half of the radioactive nuclei of a sample to decay. Now, scientists have discovered that different atoms have different half-lives. That means that different atoms have different decay rates. Decay rate is the amount of nuclei in a given sample that will decay over a certain time. So the way we measure this most of the time is in something called becquerels, which is the amount of nuclei that will decay within a substance or a certain element, a sample size of an element, within a second. Here's one example of half-life being used in the medical field. So let's say a doctor injects patients with iodine 131, which has a half-life of about 192 hours. Out of a dose of 20 milligrams of iodine 131, only 10 milligrams will decay, which is half of it, in the first 192 hours. And then 5 milligrams in the next 192 hours, and so on. We just keep on halving it. So if we were to graph this scenario with the iodine, we would end up getting a graph that looks like this over here, where my y-axis over here is going to be my iodine 131 remaining, the mass of it, and they put it in milligrams. Whereas my x-axis is my time, like normal. So if I look at this here, we started at, let's say, 2, and here we have milligrams, and that's going to go all the way down to 1 as our half-life. And then we trace across, and we're going to go then down for where it hits the graph. We end up getting 8 days. So 8 days is approximately 192 hours, and that's going to be my half-life. Then I look at half of that is 0.5, and I go all the way across, and then down here for where it hits, I'm going to end up getting 16 days, which is nicely working out. So my half-life is halving every time. So interestingly, mathematically, since this is an exponential regression, while I will keep on going on and on forever and get infinitely close to 0 on the y-axis, so a 0 mass, we'll never quite hit 0. It's always going to be halving, 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 so we can't quite hit 0 mathematically, which is kind of interesting. Now, this side here on my y-axis, we could also put things such as becquerels or my rate of decay in here instead of mass. They are all working the same way. The half-life works for all of those equally well. So now we're going to be doing some examples involving half-life calculations. But before we do that, let's go over this formula of half-life for those of you who haven't seen it before. So here we start off with my capital N over here represents the number of radioactive nuclei still remaining in the substance. Whereas N naught, look at that little 0 there, think of this as the original amount of nuclei in my material. Now the small n stands for the number of half-lives, where the 1 over 2 is, well, half of the life. Now sometimes you'll even see this equation kind of like this, where you'll have, instead up here of an n, you'll have a t, and you'll have a t 1/2. So this is representing about the amount of time, and this is the time of a half-life. So you may see this equation written like that as well, which we'll get into later with some examples. So here in my first example, we have carbon-14 with a half-life of 5,730 years. We want to know how long it will take for the quantity of carbon-14 to drop to 1/8 of the initial quantity. So what is given is that we know that my new amount of nuclei is going to be equal to 1/8 of the original amount of nuclei. We also know the half-life of this is going to be 5,730 years. Okay. Now we're going to look at my formula where we are going to have my new amount of nuclei is equal to the original amount of nuclei times 1/2 all to the power of, in this case we're going to have my time divided by the half-life time. So time elapsed divided by half-life time. Now, the key thing here is we said what n is equal to, so what my new one is. So all of this is equal to that. So in other words, I could say 1/8 is equal to just through a quick substitution. Now, if I simplify this, we know these n naughts or my original amount doesn't really matter anymore. So we're just looking at 1/8 is equal to 1/2 of, okay? So now let's plug in what we know, the variable we know. We know the half-life. So I'm going to have 1/8 is equal to 1/2, and we're going to have t all over 5,730. Now to solve this, here's the trick. Where those of you who took Math 30, you'll find this pretty simple. What we need is common bases, right? And here we have a base of 1/8, and here we have a base of 1/2. But 1/8 can be turned to 1/2 because 1/2 multiplied by 1/2 multiplied by 1/2 is equal to 1/8. So this is essentially 1/2 to the power of 3. Now that my bases are the same, all we have to do is make the exponents equal each other. Because the only way these two sides of the equation can be equal is if this exponent is equal to that exponent, since they have the same base. So that way we know 3 is equal to t divided by 5,730. So we solve for t, and I'm going to end up getting 1.719 times 10 to the 4 years. Now here are two questions that you should try by yourself. So pause the video, here are the two questions, and here are the solutions to those two questions. So in our next example, we are looking at radon-222, which has a half-life of 3.82 days. What percentage of the sample of the isotope will remain after 2 weeks? So now we're trying to find percentage. There's two ways of doing this. Our first way is we could make my original sample equal to 100. That way, if we're saying 100, and remember percent is per 100, we want to know is how much is left out of that 100. So per, how much is going to be left per 100 of these. So all we have to do is make this equal to 100. Okay? Now, we also know n is equal to my time divided by the time of the half-life. So I have to figure out what is the time and the half-life time, which is given. So my time is equal to 14 days, which is 2 weeks. And we know what is my half-life is 3.82 days. So now let's do my substitution, which will end up giving me n is equal to 100 1/2 to the power of 14 over 3.82. Now when I calculate that, I'm going to end up getting 7.9, which is 7.9%. Another way you could do this is you could just isolate for these two here, because a percent is one thing out of the other. So we want to know how many of this we have, and then we times that answer by 100. So I could have just isolated, so I have n over n naught is equal to 1/2 to the power of n. So I could have done it this way as well. So here are some questions for you to pause the video and try for yourself, and that will be it for the rest of today's video.